We'll begin our Internet Protocol discussion by talking about IPv4. So first, before we talk too much about IPv4, it's important to understand how IPv4 addressing works. Basically, an IPv4 address is are 32 bits. So it's 32 bits subdivided into four 8-bit values called octets. And octets, if you have 8 bits, of course, your range would be from 0 to 255. And that's why each octet of an IP address is limited between 0 and 255. So basically, a subnet masks, we're going to talk about this in a little bit, are also 32-bit numbers that determine how many bits are allocated to a network ID and how many are allocated to a host ID. And I'll talk more about that in just a few minutes. So when written in binary, the ones in the subnet mask that correspond to the bits in the IP address, meaning that the matched bit locations are part of the network ID. And we'll see how this works. So take a look at this example here. The IP address you can see there in binary. And the subnet mask is also in binary, where you have ones on the subnet mask means that is the network portion of the address, and where you have zeros, it is the host portion of the address. Hopefully this was covered in much greater detail in a networking course, so hopefully you got a good understanding of this, which is a prerequisite to this course. So I'm not going to talk about this too much, but just kind of a refresher on exactly what an IP address is. And of course, IP addresses are made up of ones and zeros, right? Because it's all binary data. And you probably learned a little bit of binary math in some other classes, but just as a quick refresher, if you wanted to calculate what a number would be in binary, you can do so with this example here. You just have to remember that in binary, each place is to a power of 2. So 0 to the second power is 1, 2 to the second power 1 to the second power is 2, and so forth and so on. And you can use that to calculate the binary or decimal equivalent between different numbers. So once you do that, once you have an understanding of exactly how to do that, then you can figure out what those binary digits look like. Now, in practice, we don't typically have to use binary numbers. We don't have to understand binary math in our day-to-day lives when we work with networks, but it certainly is good to understand it from that level when you're looking at how IP addresses work. So again, I'm going to kind of just skip through some of these slides here, which are a review of what's in your textbook and should be reviewed from previous courses where you've learned more about IP addressing. And in those courses, what you should have learned is that there are different classes of IP addresses, starting with a class A address, which starts with the first octet being between 1 and 127. So in this case, the IP registry assigns the first octet, meaning that if you request a Class A address, only the first octet is given to you, and the last 3 octets are assigned by you. So you have complete control over the last 3 octets. These types of addresses are intended for very large organizations that need millions and millions and millions of IP addresses. You have a very large address space with a Class A address. A Class B address, on the other hand, which starts with an octet between 128 and 191. This is where the first 2 octets are assigned by the Internet Registry, and the third and the fourth are assigned by you. And this would be for medium to large networks. So this would give you a tremendous number of IP addresses, but not as many as a Class A address. So it's kind of the middle of the road. And then finally, you have a Class C, which starts between 192 and 223. These are the IP registry assigns the first 3 octets, leaving you with 250 hosts for the host portion of the address. So again, much smaller than the other ones, but probably more efficient if it's not a huge organization which is requesting an IP address. Class D and Class E are kind of special. So a Class D is where the value of the first octet is between 224 and 239, and those are reserved for multicasting, so they're not used to assign to hosts. And Class E is between 240 and 255 for the first octet, and these are for experimental use, and they cannot be addressed. They cannot be assigned, rather, by IANA. So that's a Class E. So that kind of leaves us with a finite number of IP addresses. So IP addresses, of course, the internet's pretty popular, right? Everyone needs an IP address, but with only 8 bits per octet, right? We have 4 octets. It's really not a lot of combinations of ones and zeros. So we have a very finite number of IP addresses available, and plus we lose so many of them to the experimental space and to private IP space. So a series of addresses have been reserved for private networks where we don't need a public IP address on every single computer in our networks. And I think most of you probably are familiar with this concept because in our everyday lives, this is kind of how things work now. We all have private IP addresses. They either start with 192.168. something or 172.16 through 31, or they start with dot 10. So those are the private IP address ranges. And most IP addresses that you work with in a network probably have those ranges. When I was in Drexel University, when I started at Drexel as a student a long time ago, every single computer in Drexel University had a public IP address. So Drexel had a pretty large, I'm guessing they think they had a, let me see, it started with 144, so that would have been a Class A subnet. So they had a Class B subnet. So they had Class B addresses, which means they had those, the entire second set of octets to work with. So that's a pretty large number of addresses, and they owned all of those addresses at Drexel. Every computer got a public IP address. That has since changed. Now, in most cases, when you sign into a computer at Drexel University, most of them get a private IP address now. And hopefully at some point their plan is to return that Class A subnet back to IANA for use for other networks, for example. So using private IP addresses has allowed us to expand the range of IP addresses that we have available, because every network can have the same sets of IP addresses as long as they're not trying to route traffic between those networks, which even then you can kind of do some tricks to allow that to happen. So private IP addresses. So another type of private IP address is a link local address. So if you ever use a computer and you try to use DHCP, and we're going to talk more about DHCP later on, but if you can't contact DHCP, your computer will assign its own IP address without using DHCP, and that's an APIPA address, and typically they start with 169.254. So that's another range that we really don't have available to use for IP addressing on the public internet. It's another private range, but that's what APIPA addressing is. So if you ever see that address, by the way, 169. something, that's usually a good indication that your computer was not able to get to a DHCP server to assign an IP address to itself, or to get an IP address. So if we're going to use these private IP addresses, then we have to have a way to communicate with the wider outside world. So that's what network address translation does for us. It translates our private addresses inside our network to public addresses that are outside our network. In other words, if I make a request to google.com for a web page, Google can't communicate with me on my 10. something address or my 192.168.5.3 address. So my router or firewall has to translate that to a public IP address. And when the response comes back from Google, it has to know that that response goes back to my computer. And there's a variety of methods that a firewall would use to do that from a technical standpoint. But that's what NATing is. So NATing is what allows us to use those public IP addresses with our private IP pool within our networks. And just here's a pictorial example of what that might look like. You've got internal computers with their own IP addresses, and that firewall or that router that you see there in the middle will statically use those two public IP addresses for each of those two machines. And there are different ways to do this. So this is network address translation, but there's other methods that can do this dynamically so that many different computers can share the same public IP address, which is a little bit more useful. It's not typical that we're going to do a NAT for every single computer on our network. It's more typical we use things like port address translation, which we'll talk about later on. So classless interdomain routing, or CIDR, is basically, we talked about all of these different classes previously. So we talked about class A, B, and C. But what if we just scrap all those classes and do our own thing, right? And that's what a subnet mask allows us to do. So when you look at an IP address, I could tell that Drexel's IP is 144.something.something.something is a class B address because it's in the range for class B. But theoretically, the college could divide those itself into many smaller networks and use classless interdomain routing to do that. So you can make up your own subnet mask, and typically those subnet masks. So usually when we look at it on an IP address, for example, on a private range IP address, you'll see 255.255.255.0. And what that means is that the first 3 octets are utilized for the network portion of the address, while the last octet is being used for the host ID, or the host portion of the address. But with CIDR notation, we can use any number that we want. We can use any number of bits for the network and host portion. So we can shift that delineation between the host portion and the network portion, and we can even shift that or delineate that between those, within those octets. So you don't have to do it along those octet delineations. In other words, halfway into the third octet, I could switch from the host address to the network address. And the /n is how we note that. So for example, if I were showing the 172.31.210.10 address, which has a subnet mask of 255.255.255.0, I would show that as in CIDR notation as /24. The /24 meaning if you multiply the 8 bits for each portion that's network, right? So the first 3 255s are each 8 bits, multiply that times 3, then you have your /24. Likewise, if I were using more than 24 bits, so if I were using a portion of that host octet for my network portion, I could have, say, /26 instead of 24, meaning that 2 of the bits from the host portion are also part of the network portion and not the host portion of the address. So again, we don't always have to delineate these across those dots or at those dots. A broadcast domain defines which devices must receive a packet that's broadcast by any other device. So a broadcast packet is addressed to all computers within a network. And TCP/IP communication relies on broadcast packets. They're used to get information on the network. So if I'm trying to find the node on the network that I want to communicate with, I can send a broadcast to say, hey, who owns this MAC address, for example. And then whoever owns that MAC address is going to send me back their information. Or likewise, here's an IP address. Somebody tell me what your MAC address is. That way I know how to address those at the frame level. So broadcasting is important. So subnetting is a process that reallocates the bits from the IP address host portion to the network portion, which I talked about just a few minutes ago. And this is how we can divide a very large network into many smaller networks. And this helps us conserve IP addresses. This way we don't have to have a pool of, say, 1 million IP addresses in a network with 1,000 hosts. We can use subnet masking, so that way we can only we only have 1,000 hosts available in that network, and then we have all the rest of those addresses available to assign on other networks. So it allows us to more efficiently utilize those IP addresses that we have. So first we decide how many subnets we need, and each router interface connection indicates a required subnet. Then, in other words, every router, every connection on a router is a different subnet. And then you decide how many bits you need to meet or exceed the number of required subnets. So basically, you do all this math, and you basically come up with how many subnets you need, and you can reallocate the network and host portion of the IP addresses to make the most sense on your network. So here's just a simple example of this. So in this example, someone has divided our network into 4 subnets. And you'll notice that we had to have a subnet, so subnet D only really contains 2 IP addresses. It's the subnet between those 2 network devices, between those 2 routers. So sometimes something like that does have to be done. But in this case, we have our 4 subnets, and so we have subnet A, B, C, and D, and perhaps this could be done by subnetting. So the network number we have is 192.168.0.0, right? So that's what we have to work with. So we can start with that, and we can subnet that into different networks, and then distribute or allocate those network addresses to each one of these routers and DHCP servers throughout our network. All right, so to calculate a subnet mask based on the host address, you can do that. There's calculators online to do this as well. Again, I don't want to spend a lot of time going into how to do this because a networking class would do this. So hopefully you already have a good understanding of how this works. And if not, there are calculators online that you could certainly use. And you could also, in our textbook, there's a pretty good explanation on how that works. Now, supernetting is sort of the opposite of subnetting. With supernetting, you're basically, instead of subdividing a network or an IP address into smaller networks, instead you're taking a bunch of smaller network addresses and combining them into one huge network. So you can go the other way as well. This is not as common. Another name for this is route aggregation or route summarization. But basically it allows you to take many small networks and combine them into one large network address. So that's basically what a supernet is. All right, so for IPv4 addresses, so every IP address configuration must have a subnet mask. All hosts on the same physical network must share the same network ID in their IP addresses. In other words, if you have a bunch of computers that are connected to the same physical switch and you want them to be able to communicate, they have to be in the same network. So they have to have the same network ID and the same subnet mask in order to communicate. So all hosts, so every network address must be unique in our network. You can't have duplicate IP addresses within a single subnet or a network. And you can assign an IP address in which all the host ID bits are binary 0. If you do that, that's not a valid IP address. You also can assign an IP address where all the host ID bits are 1. If it's all zeros, that would be a network address. And if it's all ones, that's typically a broadcast address. So those are reserved and you can't use those. But everything in between, you can use that. So the Windows operating systems allows assigning multiple IP addresses to a single network connection. This is sometimes called multi-homing. So basically, you can assign multiple IP addresses if you have different computers in different networks that need to access the same server, for example, or you can use it as a router. The computer is connected to a physical network that hosts multiple IP networks. You can also use it for fault tolerance and things like that. So a default gateway is almost always used with IP addresses. This is what allows your computer to contact your router in order to get to the wider network. This would be kind of like having a mailbox with no post office if you didn't have a default gateway. So you do have to have that default gateway because if there's no post office, there's no one to deliver that letter to the wider world. So just as you configure multiple IP addresses, you can also have multiple default gateways. However, when you do that, Windows has to automatically select the best metric to connect to the right gateway. And sometimes you have to give Windows hints to do that. So you can change that metric to tell Windows which default gateway you want it to use when it's routing traffic to certain networks. Windows is notoriously very bad at making routing decisions. So I think you'll find that if you're using multiple network addresses with multiple default gateways, you're probably going to have to use metrics or add static routes in order for that to work, which we're going to talk about here, some of the commands that we can use to do that. So a multi-home server has 2 or more NICs, each attached to a different IP network. So each NIC requires its own IP address for the network to which it is connected. So you might do this because it's accessed by internal clients and external clients. So you're dividing 2 different networks. Maybe it's straddling a DMZ with a, the server might be straddling a DMZ and a local internal network or a trusted network. It might be providing resources on multiple subnets within the network. It can be configured as a router or a VPN server. This is not generally recommended with Windows, but you can use it as a router or a VPN server. It certainly has the capability to be a VPN server, and many people do that. A router, I'm not so sure if you'd want to use it as a real network router, but theoretically it does work. So multi-home servers can run into routing issues because you have these multiple default gateways, as I explained before. So the route command is what you're going to use to configure routing in your Windows server. So if you are straddling multiple networks, you would use the route command. It'll show you some information about the different routes that are available or the different paths that it would use when routing IP traffic, and you can override those and you can change those and you can fix those by using the route command to change how that works. So you can change how it routes traffic between different networks. In other words, you can tell the server that if you have a packet that's destined for network A, so let's say you have a router that's connected to network A and network B, right? So your Windows server straddles network A and B, but there's also a network C that you can connect to through network A. Windows might think that you get to that by going through network B for some reason, so you can use the route command to tell Windows that all the traffic going to network C should go to network A, not to network B, so you can override that. Again, Windows is notorious for not being very good at figuring that out because it doesn't implement some of the advanced routing protocols that you'll see in routers, like in Cisco routers and things like that. RIP being the most basic, but there are lots of other routing protocols that you'll probably learn about in your networking classes that Windows simply doesn't have an understanding of because it's not designed to be a router. All right, so there's some other command line tools, NetShell, there's some PowerShell commandlets, the IPconfig command, the ping command, ARP, traceroute, NSLOOKUP. So these are some of the tools that you can use. The NetShell command is used for your firewall and for IP address configuration, so it'll allow you to modify your IP address, for example. and your subnet mask and your default gateway. So everything you can do in the user interface. So this would be a good way to say try to manage your network interface if you're on a Windows 2012 Server Core system and you're trying to use the PowerShell. But to that end, you could also just use the PowerShell. There's some commandlets in the PowerShell that lets you set your IP address configuration. It gives you a little more granular control over some of the settings on your NIC. So it's definitely a better command if you have it. And of course, if you're using Windows Server 2012 Core or Minimal, you'll have these available in the PowerShell. Then the ipconfig command is basically just going to show you what your IP address is. It'll show you all the parameters about your IP address. The nice thing about ipconfig is that you can use it to release and renew your IP address if you're using DHCP, so you can kind of force your server to go out and get a new IP address, for example. You can also flush your DNS cache and display your DNS cache, register yourself for DNS, for example. The ping command is an ICMP command that we can use to test to see if we can contact other IP addresses on the network. The ping command only confirms connectivity at the IP level. It doesn't tell you anything about the TCP level, so you'd have to use other commands to do that, which we'll talk about later on. And then the ARP command, if you recall from your networking classes, ARP or MAC addresses are used for physical addressing, and your computer has to keep sort of a temporary table of those physical addresses, and the ARP command is how you can view that temporary table for those physical addresses. You can delete all of those, you can have it rebuild that table, and you can modify that table. The traceroute command basically tells you how a packet is getting from your network to another network, so it gives you some visibility into the routing of a packet throughout your network. So it's a useful command if you're trying to figure out, where packets are getting lost or where they're getting dropped by routers and switches throughout your network. And then finally, your book talks about the NSLOOKUP command, which we can use for troubleshooting DNS issues. We're going to talk about DNS later in this course. We have a whole unit where we talk about how to configure DNS and how DNS works. But the NSLOOKUP command is a good basic command that you can use to look up a host IP address on DNS, or from an IP address look up a host name. So you can kind of do a reverse lookup. It also allows you to look at the various DNS records, which we talk about in a little bit more detail in Active Directory in the follow-on course to this course, CT320. All right, so in the next slide deck, I talked about IPv4. In the next slide deck, I'm going to talk a little bit about how IPv6 works and how we can utilize IPv4 and IPv6 within a network.